I also wasn't really well. I did think the lack of the sheets like it didn't say. But it's a legitimate problem they kind of where people graduate. So there was a but I mean.
Okay. You can start. Yeah.
So now I know that the worst.
Okay. Good. Let us start. So first, remind you what we did yesterday. So suppose we have a generating functional for whatever many-body system, say in some say state rho 0 we are interested in, and then we want to write that generating functional in terms of the integral over the slow modes, which are denoted by chi, and then some Lorentz effective action. Okay, and then I introduce this notation capital Phi and capital A, which would be collection of the symmetric background fields and the symmetric slow modes and anti-symmetric parts. Okay. And then we discussed that on general ground, from unitarity of time evolution, that will impose the following conditions on your effective action. Okay, we impose following conditions on effective action. So this is something generally non-equilibrium. Okay. Because when you look at the effective action for the partition function, etc., free energy, you don't have such kind of constraints. So these are generally non-equilibrium physics come from real-time evolution. Okay, come from unitarity of real-time evolution. And then we showed that in addition to this, which applies to any rho 0, and for systems with the time reversal and plus this local equilibrium, one can impose additional Z2 symmetry, which I can write in this following form, that this S effective acting on tilde fields should be the same as on tilde field, and this tilde is some kind of Z2 operation. Okay, it's some Z2 operation. So let me say a little bit about this condition. Just a little bit, remind you a little bit about this condition. So the basic idea is you start with the thermal ensemble. So the thermal ensemble has a fixed background temperature. Okay, so this can be considered a fixed background temperature. And now you can imagine some many-body systems in this thermal ensemble, and then you say drive it out of equilibrium by turning on some sources. Okay, by turning on some sources. And again, the effect of turning on the source can also be captured by this generating functional, as far as you treat the background field non-perturbatively. Okay, if you are able to treat this dependence on the background field non-perturbatively, and then the dependence on the source will be captured by this generating function. And then in this case, so in this case, rho 0 then can be considered as your as a rigid temperature which you define at infinities. Okay, so you have some boundary condition, and in the middle you can have perturbations, etc. Can be far from equilibrium, but beta 0 can be imagined, say, as the temperature inverse temperature at infinity. Okay, at infinity. And now from here, then we can deduce that this W then should satisfy the following condition: that the phi 1, phi 2 are related to W phi 1 tilde and phi 2 tilde, and then this phi 1 tilde, say, is related to phi 1 by some discrete transformation. So let me just say, suppose this discrete transformation is just time reversal, and then this phi 1 just related to that, and then phi 2 tilde will be phi 2, say, minus t minus I beta. Okay, so minus t minus I beta. And so your generating function should satisfy this condition. And in order for the generating function to satisfy this condition, and now you also need to require your dynamical field to satisfy certainty 2 transformation, and in order to for this to be ensured. So the claim is that if this action is your effective action satisfied is invariant under this D2 symmetry, then that will ensure that. Okay, so in the simplest case, then this chi1 will just transform similarly as this dynamic field just transforms similarly as your background field in the case which so this is for the cases the coupling is just like chi1 phi 1 plus minus chi2 phi 2. Okay, so if the coupling between the background field, say, so if the coupling between the background field and your dynamical modes are sufficiently simple, just a linear coupling, and then you can show that suppose the effective action is invariant under this kind of transformation, and then the resulting W. So this is a simple manipulation of the path integral, and then the generating function will satisfy this condition. Okay, and here beta is all the rigid background temperature at infinity. Okay, yes. Very large one, largest length scale system is lower than equilibrium. Yeah. So this is actually so the condition here is the condition here is in the because here you have non-trivial dependence on the background field, right? So the dependence on the background field give you this non-equivalent behavior. I'm asking. Am I answering you? Yeah. Did I answer what you are asking?
I don't think so.
Okay. Say your question again.
Consider a quench or something. In comparison to wait for it to equilibrate.
Yes.
At some finite time, equilibrated on some length scale, but not everywhere.
Yes. No, not yet. Not yet. We will be more explicit later. You will see what the consequence, what this means. Here, I'm just doing something formal, but later you will see explicitly the implication of this at the level of the action. And yeah. Okay. Yeah. Beta here. I'm just doing a thermal ensemble. Then I'm turning on external source. So here I have a rigid temperature, and then you can imagine this temperature to be the temperature defined at infinity. Okay, defined at infinity. And so this is for this special case. Okay, so this is for this special case. So this is the prototype, say the local equilibrium system, which you just have thermal equilibrium, but you drive out the equilibrium using some external sources. So now the basic idea is that those transformations can actually be generalized to the general case which you actually don't have such a beta 0. Okay, so suppose I consider pure state. Okay, but it's a highly excited pure state. Then I don't have a lotion of a beta 0 even at infinity. Okay, and then turns out in the more general case, you can just replace. You can in the more general case, then you don't have this anymore. Okay, then you don't have this. Then you don't have this condition anymore for the more general case. This is only for the special case for this one. So for the more general case, even though you don't have this, we assume this kind of transformation is still true, and then you just replace this by local temperatures. Okay, by local temperatures, and then again, this will impose a non-trivial constraint on your effective action, and then actually that at least for the hydrodynamic case, we will see this generates highly consistent results. Okay, and here is just a trick to see what the transformation should be like in the special case, but this kind of transformation should not depend on the global feature of your state. And then we can just do the guess. Okay. So that's the logic. That's the logic. Good. So this encodes time reversal plus the local equilibrium. Okay. So we will see a little bit more explicitly what this local equilibrium condition means. So in general, you can actually do something a little bit simpler. So in general, when we consider things vary very slowly, then you can actually also expand this beta 0 in derivatives. Okay, so you can actually expand this in derivatives, and then that transformation can be written as chi r tilde just equal to chi r tilde minus t equal to chi r t, and chi a tilde t equal to chi a minus t plus I beta 0 partial t chi r minus t. Okay, so plus higher derivative terms. So to leading order in derivative, and then you can expand those formulas. You can expand those expressions into something like a local transformation, but then combined with the time reversal. Okay, combined with the time reversal. And again, because of this combination with the time reversal, this makes it a Z2 symmetry. Rather than looks like a continuous symmetry. Continuous symmetry. Good. Okay. So now we will discuss an example. And this example is very simple. And so what we will be doing is more like it's overkill. It's more like using a big cannon to try to kill a small bird. And but this example will be very illuminating. Because it actually illustrates many features of much more complicated series. Okay, so now let's look at this small bird. So this is the Brownian motion. At least we are not using a nuclear weapon. We are only using a cannon. Okay, so let's just consider such a Lagrangian. Say we have a free particle, and then you have a bunch of harmonic oscillator. So let me just using a harmonic oscillator, which I denote using Q. But there's a coupling between them. Okay, so just there's a linear coupling between them. And the coupling for each oscillator can be different. Just something like that. Okay. So this theory actually has a symmetry. So this theory actually have a shift symmetry. So this is invariant on the x goes to x plus constant. Okay. So the reason you have a shift symmetry is that when you shift x by a constant, and then you just get a bunch of linear terms in Qi, and then the linear term Qi can be absorbed into here, then just corresponding to shift each Qi by a constant. And that does not affect your physics, okay? And so here, even though it depends on x explicitly, but actually there's a shift symmetry, okay? There's a shift symmetry. And now let's just try to do this. So we put this on this double contour, okay? So we put this on CTP contour. So you just have dx1, dx2, then you have dqi1, dqi2, everything becomes doubled, and then you have IS1 minus IS2. Okay, so this is your fundamental theory, and S is constructed from here. Okay, and now let's just integrate out the Q, and then you just get the effective action for X1 and X2, and then you will just get X1 and X2. Okay, and so this is in the thermal ensemble. We take the 0 to be thermal ensemble. Okay, take the 0 to be thermal ensemble. Okay, and so now let's just try to use our general principle to write down this S effective. Okay, to write down this S effective. And yeah. So so now let's just go back to the conditions. Okay, so we will again use the variable XR and XA. Okay, we will use variable XR and XA, which is a symmetric and anti-symmetric combination of X, and we will just write this action in terms of that. Okay. So and also here, because everything is quadratic, and then the effective action will also be quadratic. Okay, this is something you can do exactly actually, but here we are just trying to write it down using derivative expansion. Say suppose everything varies slowly. And so this S effective will only contain quadratic terms. Okay, there's no higher order terms, only quadratic terms. So now this, so XR, XA. Okay. So first we can first let's try to write down terms which are with 0 derivatives. Okay. And then remember from this condition. Sorry, here should be phi r. From this condition, there can be no term with only phi r only. So any term must contain at least one factor of phi chi a, xa. So the simplest term you can write down is xr xa, then xa squared. Okay, so without derivative, that's the simplest term you can write down. But now we have to impose this symmetry. Okay. Symmetry, this is the global symmetry. Then that means this action should be invariant on the simultaneous shift of x1 goes to x1 plus a, and x2 goes to x2 plus a. Okay? In other words, this should be invariant under xr goes to x. So it should be invariant under xr. Yeah. xr goes to xr plus a, but the xa does not change. Okay? Because they cancel, okay? Because they cancel. Then that means this term is not allowed, okay? Because this term is not invariant under such a shift, okay? Under such a shift. But this term is allowed. This term is allowed. And this makes sense because this term, if you write it in terms of ordinary language, this corresponds to x1 squared minus x2 squared. And this corresponding to actually generate a harmonic potential, and this should not happen here, okay? Because this is a particle just coupled to some bars. This should not generate such a potential. So this term is not there, but this term can be there, and this term, according to our rule here, then has to be pure imaginary, because this term is even in XA. So even in XA, that means the S effective minus phi A is equal to itself. And then when you take a common conjugate, then there's minus sign. So actually, then there's so there must be I here. Okay, so let me just write I sigma. Okay, so sigma is just some number. Okay, and so this must be yeah. And now you can write down terms with derivatives. So for example, the one derivative. So again, you can write down such term xa. Partial t xr, and so that's the only term you can have with one derivative. Yes. No, you cannot. It's because this is a global symmetry, and when we do this contour, so when we do this contour, So this is the contour which the x1 should be identified with x2 at infinity. And so if you make this kind of independent shift, then that will violate that boundary condition. So they can do so you can only shift. So you can only have diagonal shift. Yeah. Yes. Yeah, that's possible. But here it's sufficiently simple. That's the only term. The linear. Here, linear XR term is not possible because because you cannot have terms which only depend on XR. Okay, you might consider there's a linear XA term, and the linear XA term. Let me think. Yeah, linear XA term. Maybe you can. It can be absorbed. And also the XA term, I think, will not be generated because I think everything here will be quadratic. Yeah. Good. So you will have this, and then the first due to all the term, then the only term would be this term in terms of single A. Okay, in terms of single A, and you can also have the two derivative terms, say with m xa dot. Yeah, let me just all use the dot, okay, to denote the time derivatives, and xr dot. And you can also have the xa squared term involving derivatives. Let me just now write them down, okay. Anyway, so that's the term you have, okay.
What's the argument that
Yeah, so XA term you may combine with this term, and then corresponding to shift XA by constant, and also maybe in the original Lagrangian, when you integrate things out, I think there's no linear term will be generated. Yeah. Sorry. Yeah, XA is in principle linear term XA is allowed. A linear term in XA is not in principle. Yeah. Oh, we can even add XA term. I think this does not do anything. Anyway, yeah, let's not worry about XA term. Yeah, yes.
Which of the signs of these parameters are?
Yeah, I will tell you. Okay. So now that's what we have. So the key thing is that this term is imaginary, and the term linear in XA would be real. Okay, term linear in XA will be real. Okay, and then you can write higher order terms. And now let's use in this condition that the imaginary part of action should be greater than 0. Okay, and then that will tell you that the sigma should be greater or equal to 0. Okay. Sigma should be greater or equal to 0. Oh, it's because so this term is even in the XA go to minus XA, and then if you look at this condition, there's a minus sign here. So this if this is even in XA go to minus XA, then star give you a minus sign, and then have to be pure imaginary. Okay, pure imaginary. Okay, very good. So, and then we find that sigma has to be greater than 0. And now let's impose this condition. Okay, say the action have to be invariant under this transformation. And then you can just apply this one, okay? You can just apply this, just replace this by x. And then you find, then there's a relation between them. Then you find that condition applied to here tells you that the nu with this sign, okay, has to be equal to sigma times beta. Okay? So this is from 4. Let me just say this is from 4. This is from 2. Okay, this is from 2. And 4 tells you that so it's a simple exercise you do 4, that the 4 nu have to be related to sigma times beta. And that tells you that nu should be also be greater equal to 0. Okay? Okay, that tells you nu should also be greater equal to 0. Okay, so now let's see what this theory tells us. Okay? Now let's see what this theory tells us. To convert this into something a little bit more familiar form, so let me do a Legendre transform for the XA. Okay, so let me just write down. So let me do a Legendre transform XA. I write sigma XA term into 1/2. I introduce a new variable psi times XA. Okay, and so if I integrate over psi, and then that will generate the XA terms. Okay, here should be understood under the path integral. Okay, in the exponential. Okay, when I write equal, should be understood within the path integral when I integrate the maybe not write equal, just write. I can do that. So now, with this, then now let's write down the path integral. So now the path integral have the following form. I have dxa, dxr, dxi, and now I have exponential I dt. Let me just plug in this action, okay? Except now I just replace this term by this term, okay? So let me just do that. So we have nu xa xr dot plus mxa dot xr dot term plus 1/2 I sigma psi square plus psi xa's. Okay? Okay, good. So now you see the dependence on xa is linear. Okay, now you see the dependence on xa is linear. So that will just give you a delta function. Okay, now the dependence on xa, would be given by let's do integration by parts. So it will give you minus xr dot double dot minus nu xr dot plus psi. Okay, so this is a dependence there. Okay, in the exponential will be I then plus something else. Okay, and there's the only term just this term. Let me just write it down. 1/2 I square. Okay, and now this just become Lagrange multiplier. Essentially, this just become, when you do the path integral, this just become a delta function minus mxr double dot minus plus nu xr dot plus psi, minus psi. And then you have this Gaussian. Now this I and this I, now this I is crucial, now become a Gaussian. Okay? Become a Gaussian. Okay? So we see the original I here is crucial because this I leads to this I. And this I, and then when you put when you multiply I, then you get that, and then it's good that the sigma is actually a positive. Okay, and so this condition ensures you actually have a well-defined the Gaussian integral. Okay, so now this system just becomes something we're familiar with. So now we just have an equation motion. And this just means we just can evaluate this as equation motion. Psi. And then this psi is a stochastic force. Then we'll have a Gaussian distribution. Okay? Yeah, because psi have a Gaussian distribution. Okay? Yeah. And the relation now between this sigma and that nu. So now you see this and then nu. So this is just Einstein relation. Okay. So the relation between nu and the beta sigma. So this is just the Einstein relation. So from there, let me just write it there. And then this is just so this is a standard stochastic equation for the Brownian motion, this is a friction term, which does have the right sign to be positive, and this is a stochastic force with a Gaussian fluctuation controlled by sigma, and then the relation between the friction coefficient and the sigma is precisely the Einstein relation. Also, it's the standard so-called fluctuation dissipation relation. Okay. So that just becomes the standard fluctuation. Yes. Oh, you can include higher order terms, and then that just include you put some higher derivative terms here. Oh yeah. Normally, when you truncate, is that you have to look at your theory, then you ask yourself what are the relevant terms, and then you truncate, and then to lowest order you only include those relevant terms, say under RG. Yeah, because this is the path integral, and then you try to assign the dimension to various fields, and you say what are the relevant terms, etc. Here, I'm just giving you an illustration for this simple. Yeah.
I was still kind of confused about the previous question.
Yeah.
What is beta? So I'm assuming you want temperature to vary much more slowly than background fields.
Now in here, the beta, for this particular example, beta is just a constant beta. Beta we are allowed to vary when we include the genuine hydrodynamics. So here is just the particle moving in the thermal bath. And so this is just really just a probe particle moving in the thermal bath. And then later, when we really think about the whole system, and then we will introduce the local temperature as a dynamical variable. Yeah. Okay. Other questions? Yes.
Sure. If I did sign,
Yeah, it's the same thing. Yeah, it's the same thing. Just I do this just to tell you. There are several lessons I want you to learn from here. The reason that I write in this form. This also just makes into the make a connection into the traditional form of the Brownian motion. Yeah. Okay, so now let me summarize what the lesson we learned from here. Okay, so the lesson from this simple example. So the first is that generically under our condition, under those conditions, those are the only consistent conditions we need to add, and we find that generically contain dissipative terms. Okay, as expected, contain dissipative terms. Okay, and then, so this is the first lesson. The second lesson is an imaginary part of the action controls fluctuations. Okay, so we see that this imaginary part of action now become the essentially the Gaussian fluctuation of this stochastic force. Okay, and so the imaginary part controls the fluctuations. And the third. So let me give a name to this equation. So we call this this condition the dynamical KMS symmetry. Okay. So this dynamical KMS leads to the standard fluctuation dissipation relation. Okay, leads to the standard fluctuation dissipation relation. And the 4 is that the condition 2, the imaginary part of 0 leads to the right Gaussian the right sign in Gaussian fluctuation, and through this fluctuation dissipation relation also the right causality. Okay, so here the causality means that the behavior of this is retarded. Okay, it's retarded in nature. So the right causality. Okay. To write causality to the causality, and yeah, and number 5. So now, if you look at this equation, so this is the standard stochastic equation for particle. Okay. So now from here you deduce that the XR. So previously we have 2 copies, X1 and X2. So which copy corresponding to the physical one? Okay, so now we know. So the XR is the really the physical motion. Okay, describe the physical motion. It's really the what you should identify as the coordinate of the particle. There's only single coordinate, single copy, and the XA is conjugate to this stochastic force. Psi, okay? So the psi is just a stochastic force, so this is a force, and XA is the conjugate to that. So this tells you this corresponding to stochastic. So XA. So XA means that should corresponding to some kind of stochastic position noise. Okay. Okay. And yeah, because this is what is conjugated to a stochastic force must be a stochastic coordinate, and XA. So XR is your genuine physical motion. But on top of that, there's actually also some kind of position noise, and this is XA. Okay, and so this example also tells us generically what is the interpretation for the chi-R and the chi-A. It's always that this corresponding to the physical quantities you are interested in, and this chi-A corresponding to the noise of the corresponding observable. Okay, of corresponding observable. So now we see interesting that in the real-time formalism, now the fluctuation of a dynamic variable separated into 2 types. One type is the fluctuation of the dynamic variable themselves, and also there's another type corresponding to their noise. Okay, corresponding to their noise. Just to include the fluctuation of dynamic variable themselves is no longer enough. Actually, you actually have to include the noise. Actually, at this quadratic level, actually there's no fluctuation for XR. Okay, no fluctuation for XR because all the fluctuation is determined by psi. So only fluctuation for XA. But if you have a cubic theory, such a higher nonlinear theory, then XR itself will also have non-trivial fluctuations. Then it won't be a delta function. Okay, then for nonlinear theory, and then there will be a non-trivial fluctuation of XR also. And so generally this physical variable actually have 2 types of fluctuations. Yes.
Yeah. Well, the
That's a very good question. So fluctuation dissipation theorem so this is like a fluctuation dissipation theorem at the 2-point function level. A fluctuation dissipation theorem at the 2-point function level does not lead time reversal. But if you go beyond the 2 points, then you do lead it. And the reason is the following. The reason is that this is related to what I said yesterday. This is what I say that so when you do the KMS, you relate this W to WT, which is the time reversed one. Actually, at the 2-point function level, they are the same. The WT and the W, they can be actually be raised, they can be identified. be identified. But beyond the 2-point function level, they cannot. And then you have to use time reversal. Yes?
So if we took a different potential other than a harmonic oscillator potential, would this
No, this conclusion will not change. So this, you mean this conclusion? Yeah, will not change. Still, this XA always acts as some kind of noise.
Irrespective of what?
Yeah. Actually, I will now talk about this point. Yeah, now I will talk about this point. Good. Any other questions? Good. So now let me just make some general remarks based on this 5. Okay, so maybe make some general remarks. So now let's consider a general. Now it's a number. Yeah, let me just put it as number 6 as a general remark. Now let's consider general theory. Okay, so again, now I will have this chi r, phi r, chi a, phi a, and the phi again corresponding to the sources, and the chi corresponding to the dynamical variable. And the physical sources, of course, normally when we talk about the physical problem, we turn on some external source. So the physical source would corresponding to just phi r equal to some phi, and the phi a equal to 0. Okay. So so for the physical source, actually the two legs must be the same, because if you turn on some external electric field, it must be the same. So the phi a is more like a trick, mathematical trick to generate correlation functions of R variables. Okay. So this is this does not have direct physical interpretation. Okay. And now, so now let's consider the following situation. Okay. Consider in the presence of the physical source. Okay. So now let's consider the general structure of this equation motion. So the general structure of equation motion, let's look at S effective over the chi a equation motion. Okay. So this is one equation motion. Okay. And this, due to this condition, so remember phi a is 0. Okay. Phi a is 0. So now due to this condition, then this effective action must at least contain one factor of chi a. Okay, must contain one factor of chi a, because phi a equal to 0, and because so that means this, when you take derivative over chi r, must contain one factor of chi a. Okay. And also remember the boundary condition for chi a is at infinity, at t equal to infinity, the dynamical variable should be identified. Okay. So that means chi a at t equal to infinity is 0. Okay. And so that means you can solve this equation consistently just by setting chi a equal to 0. Okay. Just by setting chi a equal to 0. And this would be the simplest solution to satisfy your boundary condition and equation motion. And now let's look at another equation motion, just S effective over chi a. And now you can just set chi a equal to 0 now. Okay, you can set equal to chi a equal to 0 now, because and now this equal to 0, and this is your generating physical. Now you only have one copy of modes now. Okay. Now you only have one copy of modes, because chi a is set equal to 0. You only have chi r, and then this is your normal dynamical physical equation motion. Okay. Yeah, this is the physical equation motion. Okay. This corresponding physical equation motion. So we can but this equation motion But then in this equation motion, there's no fluctuation, okay? Because in here, there's no fluctuation anymore. This is just corresponding to your standard equation motion. So if you do this for this example, then you will just get you will just get this equation with psi equal to 0, and you will just get a particle moving with a friction, okay? And if you want to see this stochastic term, and then you have to include the Good. Okay. So now with this, yes.
Could there be other solutions like phi is not zero and slope at the same time? Which doesn't really have
personally I don't know. Personally, I don't know any example which happens. But if you say have phi a not equal to 0, and then this can depend on phi a, then phi a can source chi a, and then this is no longer true, and this is no longer true, and then for example this can be used when you turn on the phi a, then that can be used as a trick, say to find certain correlation functions. If you want to find the phi a dependence to find the generating functional, and then you actually have to turn on phi a, then chi a in general will be non-zero. Yes.
That's the reason why the physical source couldn't just put sources on.
So the physical source. So this contour is a mathematical construct. So if you just think about a single space-time, we just turn on some source. And then when you translate that picture into this picture, and then these two must have the same source. They must have the same source. And only when we play the mathematical trick, then we can put the source different. And then that will generate some give rise to some generate. That just used as a mathematical trick to generate some correlation functions. Yeah. No. Actually, it's both of them. No, it's both of them. Yeah, because you see, this is U and U dagger. In the physical evolution, U and U dagger is the same. So going in this direction is U, going in this direction is U dagger. Yeah. Yes.
So you said you were describing this and looking at the equation motion with
Yeah, pure. Oh, right. Yeah. So here you don't. If we do this, you don't have to introduce C. Then you can just do the equation motion here. Okay, just do the equation motion here, and then you set XA. Yeah. So you obtain equation motion and then set XA equal to 0, and then you will just get that. Yeah, you can see when you do equation motion, and then this gives you X double R term. So this gives you a friction term, and then you get the XA term, and then when you set XA equal to 0, then the source is equal to 0. Okay. Sorry?
How do you actually get the stochastic equation?
Stochastic equation because I keep the full path integral. Because here I keep the full path integral, I didn't do the settle point. So the solution corresponding to the settle point. Yeah, so I also included the fluctuation. Yeah. Yes? No, it can be far from equilibrium. Any hydrodynamic situation should be, in principle, should be able to describe. Yeah, that's a very good question. So this formalism, when you apply it to the non-equilibrium hydro situation, will give you a local fluctuation dissipation relation. Just locally you have fluctuation dissipation relation, but not globally. No, actually, any state. Yeah. Even for the steady state, I think this can already be interesting. This can already generate the result we normally. Yeah, because normally you have to guess. So normally when you do fluctuate, when you do stochastic hydrodynamic, you have to guess what you put on the right-hand side and how to put this in. Once you are far away from equilibrium, how to do that is it's not clear how to do. But here we will be able to systematically derive that. Yeah.
What does that do? Does it allow us to do everything?
That allows you to do any situation which can be described by the standard hydrodynamic situation. because the standard hydrodynamic situation precisely assumes that, at least in the equation motion. And but this cannot describe, for example, this Carter-Paris-Zhang equation. This Carter-Paris-Zhang equation is very tricky. It does not satisfy this equation. It does not satisfy this equation. And then how to generalize to that case is actually a very interesting question. Yeah. Yes. Yeah, it will affect. For example, you will see, say, for example, they come in the parameters of your, action, right? For example, here. So, for example, here the coefficients depend on beta. For example, nu are related to sigma beta, and beta is a parameter which goes into the density matrix. Sorry, say it again. The density matrix, in this case, the simplest we can just take to be this one, to be the thermal one. Then, it does depend on that. Yeah. Yeah, it is important to get rid of the potential term. Otherwise, you will generate. Otherwise, you have to add the potential term. Sorry, say it again. Yeah, right. That's right. Yeah. In many theories, shift symmetry are important. Yeah, that's right. Yeah. Yes. Okay.
So imagine you have some initial state, you have some initial dynamics, and the material system that by checking out the I would imagine initial dynamics, the local, even the local fluctuation will be very different from
So that's a good point. So this is a condition should be understood as a condition which snags a class of states. And so we are here, we only look at those class of states which satisfy those conditions. And I cannot tell you precisely what class of states, okay? What class of states will satisfy this condition. But thermal ensemble perturbed by some external source is one such example. And say black hole macro state should be another example, etc. So this selects a class of states. Yes.
So I guess it's typical in hydro that if you were going to put in some fluctuations, you would get some Gaussian.
Yeah.
Can you generate
Exactly. So this formalism, then you can systematically. So the standard, of course, you can generalize this to the full hydrodynamic situation. So here is your standard hydro equation, and then this is some kind of stochastic force. But you only know really how to do that near the equilibrium. Once you are far from equilibrium, then we don't know how to write down this kind of stochastic. What's the precise form to write down stochastic force, and what will be their fluctuations? But this formalism will allow you to write them systematically. Yeah, for example, around Wilhelm flow. Yeah. Okay, good. Now let's go to the real deal. Okay. Now let's go to the real deal, and now finally let's go to the hydrodynamics. So now let's do the hydrodynamics, to the theory of conserved quantities. Unfortunately, I think, So let me first actually do a brief review of the hydrodynamics, just to highlight review of traditional formulation. Okay, that's a traditional formulation. So for simplicity, let's just consider relativistic systems. And in relativistic system, you always have a conserved quantity, which is stress tensor. Okay, if you have local field theory, and yeah, let's consider some local field theory. Then you always have a conserved quantities, which is stress tensor. Okay, and if you have some other symmetries, say for example some U1, then you may also have some other current. Okay, which is conserved. Okay, and then what we said is that all the physics in the long distance and the long time should be controlled just by those equations. Yeah, because all the slow modes are associated with conserved quantities. Okay, so this must be enough to understand your low energy physics. And this is precisely what the traditional idea of hydrodynamics doing. So the idea of hydro is to parameterize the T mu and the J mu in terms some dynamical variable okay, in terms of dynamical variables, and then let me call this star and star star. So if you can do that, and then the star and the star star, then just give you then you just equal to the equation of motion. Okay, so equation of motion just it's just your conservation equation. Okay, this means plus. Okay, this is equation of motion. So now, in order to see what are the best variable to parameterize T and J, let's first consider equilibrium situation. Okay, so let's consider equilibrium situation. So in the equilibrium, then we just have we have the thermal density matrix, beta H0, and the minus beta mu J0. Okay, and so this is your equilibrium density matrix. And then of course in this case below, that you can actually express T mu and the J mu in terms of, so I expressed, just expressed in terms of beta and the mu. Okay, so let me call this beta 0 and mu 0. Okay, and in fact you can write their form explicitly. So you can write their form explicitly. So we know that in the standard situation, the T mu must have the following form. You have energy density, which depends on mu 0 and beta 0, and then you have P mu 0, beta 0, and the P. Okay, and the rest is 0. So in your in that, and the J mu would be just equal to n, the charge density epsilon 0, beta 0, mu 0, and then 0. Okay, and J will have this following form. Okay, so now let's consider to write this in a list slightly more generally. So this is in the rest frame. Okay, so now let's imagine we write it in the general initial frame. So in the general initial frame, then I can generalize this into the following: 1 over z, then exponential minus beta T0 mu. Then I can introduce a constant velocity field, which tell me the I can write it as mu minus beta mu beta. Let me do it here. Sorry, I run out of space. Okay, and then I can just go to a general frame. In the general frame, then I can write rho 0 equal to 1 over z exponential minus beta u mu is a velocity field. It's a velocity now. Okay, define your frame, and then integration of t0 mu minus mu j0 j mu. Okay. Okay, just can be written in that form. Okay. So now in this more general frame, we can. I think I will not need this today. I think no. So in the general frame, you can just boost this behavior. Okay, you can just boost this behavior. You can just boost this behavior to a general velocity frame u mu. Okay, yeah, you can just boost that, and then of course then we get a standard expression that you have t mu mu, then just given by epsilon times u mu u nu, and p delta mu mu, and delta mu mu is equal to eta mu mu plus u mu u nu. Okay, so when you project into the time direction, yeah, so in the rest frame just become that. Okay. Okay, so now, so this is the expression for the stress tensor for the equilibrium situation in some arbitrary frame. Okay. So now let's go into non-equilibrium situation. Going to non-equilibrium situation. So now let's see, again consider a situation which things are all vary very slowly. Okay. So let me emphasize that the local equilibrium, since vary slowly, does not mean near equilibrium. Okay, can be far from equilibrium. It just have to vary slowly. The magnitude can be big. Okay. So now let's consider things are vary very slowly. Then locally, you must. Then the stress tensor then should still be able to be approximated by this form. But now you can just introduce the local temperature and the local chemical potential. Okay. So now for the non-equilibrium situation, so locally, we can just promote epsilon, or promote the beta 0 goes to beta x, now depend on space-time, and the mu 0 depend on space-time, and the u mu, the velocity, can also depend on the space-time. Okay. And then locally, this must be still valid in some local region. Okay, but of course now since they are not no longer constant, there must be corrections. Okay, so let me call this T0. T0. Oh yeah, I also forgot to write the J0. So J0 would be just n u mu. Okay. So now for the more general situation. So for non-equilibrium situation, then we must still have, then we can write the general T mu mu in terms of T0 mu mu, but now depend on x now, okay? Now depend on beta x, mu x, u mu x, but now plus the derivative corrections, okay? So so this contains the derivatives of those variables, beta, mu, and u mu. Okay. So let's just imagine that. Okay. Let's just imagine that. And this make perfect sense if beta, mu, and the velocity they all vary very slowly with space-time. And then that should be the case. Okay, you have some. And then we can just do derivative expansion. Just to expand this guy. Just expand this guy, write down the most general derivative expansion in terms of those fields. Okay? In terms of those fields. And so now we have now we have achieved the goal. Okay, now we have achieved the goal. So these are just our dynamical variables. Okay, so these are our dynamical variables. So now let's count. There's 1 beta, there's 1 mu, there are 2 of them. And u mu, so this is a velocity field. Velocity, by basically always normalized to be -1 u square. So for d dimension, these are d plus 1 variables. Okay, this is d minus 1. These are 2, so d plus 1 variables. And here we have d plus 1 equations. Okay, because here the d equations, and then there's 1 equation. Okay, so so now we have exact. So we have a closed system. So we have d plus 1 equations variables for d plus 1 equations. Okay, so we have a closed system. And so it turns out this is not quite enough. Okay, so this is a beautiful idea, and this is very nice. It turns out if you use this equation, try to describe the real-life fluid, actually you will get the wrong results. You actually have to impose some further phenomenological constraints. Okay, so there further phenomenological constraints have to be phenomenological constraint. So now you have to include a further phenomenological constraint on this derivative on this expansion, on this derivative expansion. Okay, and the constraint. So let me just say the first constraint, which I already explicitly stated, is that when we promote in the equilibrium situation, those epsilon, p, and n, they are not arbitrary. So for example, p will be, suppose p will be described by the equation of state, and once p is determined, then the epsilon and n also are determined from the standard thermodynamic relation, equilibrium thermodynamic relation. And when we extend to the non-equilibrium situation, then we are using the same n and epsilon and p. Okay, so that means we are assuming some kind of local version of the first law. Okay, so that is the epsilon beta x and mu x are and mu x beta x determined from P. Okay, so so this is the first phenomenological constraint you have to impose, because normally if you just do naive derivative expansion, then there should be arbitrary constant why you should impose such constraint. Okay, so you have to impose the local first law. Turns out this is again not enough. You have to impose actually a local second law. Okay, you have to introduce a local second law. So if you have a local equilibrium, then you can actually if you have a local equilibrium, then you can actually introduce the concept of entropy locally. Okay, because it's a local equilibrium, so now you can require the local entropy production should be non-negative. Okay, you also have to impose this constraint. So how would you do that? So the idea would be, say you postulate there's an entropy current. Okay, so there's an entropy current, and then the first term in the entropy current is still given by the equilibrium one, so which depend on this beta x, p mu x, mu. Again, this is determined from P. Okay, determined from P. And then you plus derivative corrections. Okay. So in practice, what you do is that you write down the most general entropy current, and then you look at the equation motion. Then you require the equation motion are such that such an entropy current exists, that when you evaluate it on the equation motion, it's never non-negative. Its divergence is never non-negative. Okay, so require. So these two require existence of S mu which satisfy partial mu S mu greater than 0 for any solutions. So any is key, okay, of equation motion. So this constraint is rather awkward to impose, actually, rather awkward to impose. But this constraint will limit possible terms which will appear in that derivative expansion. Okay, in particular, certain terms just eliminated. A certain term is eliminated, and then certain coefficients are related to each other, etc. Okay. And also this condition will require, say, those dissipative coefficients in the expansion to be non-negative. Okay. So this is the standard treatment. Yeah. Yes. Yeah. Now I'm describing the conventional formalism. And then I will describe that in this formalism, you don't have to impose all this by hand. They just follow from this Z2 symmetry. They just follow from this Z2 symmetry. Yes. Yeah. Yeah, here. So these are your equation motions. Yeah. Good. Yeah. So in the conventional formalism, you have to impose this first law by hand. Then you have to impose the second law by hand. Okay. And then you also have to impose the time reversal symmetry by hand. So as I mentioned earlier, the time reversal symmetry requires yeah.
Maybe somebody else is confused like I am. So you have all the stuff on this blackboard right here.
Yeah.
And you just go, a bunch of stuff is going to go away. Okay?
Yeah.
So what can be written down is going to be Y quotient. Now, at the end of like definition of T mu, the equations of motion. So up there, that's what I want to hold on to, and the rest of it you were just sort of setting this up.
Yeah. I'm just setting up.
No, I mean setting this up for a fall.
No, not for 4. It's true. Half is true. I'm just reviewing for you the standard formulation,
Okay.
and I'm pointing out the feature of the standard formulation, and then I will explain how in the effective field theory all these features then can be realized and generalized. Yeah. And the third thing you actually need to do, also imposed by hand, is you need to turn on some external source for those T mu and J mu, and then you solve for the linear response. And after you solve for the linear response, then you require the linear response matrix are symmetric. So this is called linear Unsag relation. Okay, linear Unsag relation. So again, this is a little bit awkward. You have to turn on the source, solve equation motion, find the response, and then you require the response matrix is symmetric. And then that again puts some constraint on your T mu. Okay. So now, this is the formulation of the standard hydrodynamics. So now I'm reaching the end of today. So now let me just say what we will do next time. So what we will do next time is that now I will develop a genuine effective field theory based on these 4 conditions, which I just erased. And then from those 4 conditions, in particular that the Z2 symmetry, and that the imaginary part of effective action should be non-negative, then that will take care of all these phenomenological constraints. And also will lead to, and at the equation motion level, and precisely leads to those equation motions and those expansions. Okay, just recover precise formalism, but now everything just follows just from symmetry, follow from symmetry. Yeah. So let me stop here today. Yeah.
So is the general algorithm like we have d+1 variables and d+1 equations? So we solve for all of them and then imply those constraints, or like we first imply those constraints?
Yeah. So it's a little bit tricky. So what you would do is the following. So you essentially just try to do it a little bit more formally. For example, you just write down the most general. Because key here is for any of the solutions, okay, for any solutions. If you something like this have to be true for any solutions, then God has to be that this on the right hand side can be written as a square. Can be written as a square, because otherwise you may choose some solution and this is not satisfied. And then what you will want to do is that you want to say adjust possible terms there, so that and adjust possible terms here, so that you can find such a S mu, so that the evaluated on the equation motion, the right hand side is precisely a square. And from that way, you constrain the equation motion. You actually don't solve the equation motion explicitly, and you just impose the equation motion on this quantity and make it to be a perfect square. And so this is a rather awkward and complicated process. Yeah. Yes. Yeah. Sorry, say it again. Right. Right. No. Those conditions, they don't over-constrain. They don't reduce the variables. They just reduce the number of couplings in your theory. So when I expand, so this is the zeroth order. I have those coefficients. So these can be considered as the couplings of your theory. And then I also expand this in terms of derivative into other tensors with derivatives and with different coefficients. And then those constraints will constrain those coefficients.
So in other words, it dictates the constraint on the equation that you're solving.
That's right. That's right. Yeah, because if you don't impose these conditions, the resulting equation will generate unphysical solutions. And sometimes when you say you generate unphysical solutions, we just throw them away. But here, you want that every solution makes sense, okay? Because this is hydrodynamics, and it describes real world. You want every solution makes sense, okay? You don't want to artificially say throw away some solutions. Yes?
I guess thus far I don't see why
Very good. The quantum mechanics is not, in the end, the quantum mechanics is not important, but the irony is, somehow in order to derive this classical statistical problem, it's better to start with a quantum many-body system and then take the classical limit. Because as I said yesterday, there's a constraint from the quantum unitarity, which actually is important. And also, we will see even more exotic next time, even though we are interested in this hydrodynamics in flat space. But turns out much easier to consider the hydrodynamics, to consider the theory on a general curved space-time. And actually, that will constrain you even more. Somehow, even you want to write down a theory for the simplest situation, you start with the most complicated situation. And because that gives you the most constraints. And then you go to the simple case. Yeah, it's the irony of life.
So I think all this comes about not throwing away solutions. Also, it's good to have some action.
Yeah, this formula. Yeah, because this is the because hydrodynamics governing the physics at the long distance. And so this is already highly coarse-grained. And in particular, hydrodynamics itself does not include fluctuations. So the entropy cannot go down at the equation motion level. And when you include the fluctuations, then indeed statistical fluctuations can drive the entropy go down, and but not at this equation motion level. Yeah.
Okay, so before we break, come to the cookout tonight, your okay, and I need because you will be carded. Okay, it's just like the
Oh, actually, I left in my hotel, I think.
You're a grown up, so see me afterwards.
Okay. You am a grown up, behave not like a grown up because I forgot it in my hotel. There was one question, yeah.
Yeah, I had a question. So I guess this classical versus quantum thing also shows up if you want to take care of anomalies, right?
Yeah.
Right. So I mean, if we started from the classical from the very beginning, it would be
That's right. That's right.
suffering.
Yeah, exactly. Yeah. If you want to describe the system with anomaly, and then you actually need to start with the quantum level. That's right. Yeah. Mm.
Okay.
Mm.